Real-world medical image segmentation is a challenging task, particularly for tail conditions associated with rare diseases. We propose MaxQuery for out-of-distribution localization in this task. We adopt object queries in mask transformers to formulate segmentation as a soft cluster assignment. During training, the queries fit the feature-level cluster centers of inliers, allowing the similarity between pixels and queries to localize OOD regions during inference. We propose a query distribution loss to enforce clear boundaries among segmentation targets at the query level, which improves both inlier segmentation and OOD indication. Our framework is tested on real-world pancreatic and liver tumor segmentation, and outperforms previous state-of-the-art algorithms. Real-world medical image segmentation has tremendous long-tailed complexity of objects, among which tail conditions correlate with relatively rare diseases and are clinically significant. A trustworthy medical AI algorithm should demonstrate its effectiveness on tail conditions to avoid clinically dangerous damage in these OOD cases. Specifically, real-world medical outliers refer to unseen and rare tumors, and inliers represent labeled lesions. This forms a typical and challenging near-OOD localization problem due to the subtle differences between them. Therefore, we need to address both inlier segmentation and OOD localization to achieve real-world trustworthy medical AI. Here is an overview of our framework. We build our model with a CNN backbone to extract per pixel features and a transformer decoder. This transformer decoder interactively updates the learnable object queries to fit the inlier cluster centers. Inspired by recent works on cluster analysis of mask transformers, we consider semantic segmentation as a two-stage cluster analysis process. Firstly, all pixels are assigned into different clusters based on the affinity between pixel features and cluster centers. Secondly, cluster classification guides the grouped pixels to further aggregate and generate segmentation logits. The overall segmentation is supervised by a classic segmentation loss and a novel query distribution loss. We observe that when only using classic segmentation loss, queries focus majorly on the background and organs rather than the tumors. Because the significant difference between foreground and background greatly distracts the model from focusing on subtle differences between OOD objects and inliers. Motivated by this, we propose a query distribution loss to manipulate the object queries and guide them to focus on the foreground, especially the tumors, and encourage concentrated cluster learning. This loss is achieved by merge certain channels of cluster assignments and ground truth, following by computing the negative log likelihood loss. We find this loss benefits both two tasks. We propose MaxQuery for OOD localization. Motivated by cluster analysis, OOD pixels should be far from any of inlier cluster centers. MaxQuery is defined as negative of maximal query response, which reflects the distance of a pixel and its assigned center. Therefore, MaxQuery of the inlier, dotted arrow, is usually smaller than that of the outlier, solid arrow, and thus is able to identify the anomalous/OOD pixels. We visualize the mask predictions of in-distribution and OOD examples to illustrate the working mechanism of object queries as cluster centers and how MaxQuery identifies the OOD condition. We can observe that the background and organ regions are confidently activated by specific queries. The corresponding queries of specific in-distribution tumors usually concentrate at a single center, while queries corresponding to the OOD tumors seem to split into multiple centers with lower responses. This visual examples fulfill the motivation of the proposed MaxQuery that no inlier cluster centers can dominantly fit the OOD pixels. We curated and conducted experiments on two datasets, specifically, pancreatic and liver real-world multi-type tumor segmentation datasets. Compared with anomaly localization baselines, our proposed method achieves state-of-the-art OOD detection performance at both pixel and case level. We visualize the anomaly score map for OOD localization. The grayscale level indicates the anomaly score. Our approach maintains a high anomaly score in the OOD pixels, outlier tumor, while a low anomaly score in the in-distribution pixels, organ. For inlier segmentation, our method outperforms strong baselines, especially nnUNet. Our ablation study shows that the method is robust to the key hyperparameter, the selection of query distribution. Meanwhile, the proposed query-level anomaly score is superior to the category-level score. Processing a large collection of medical imaging data with long-tailed distributions has always been challenging. To the best of our knowledge, we are the first to explore the near-OD localization problem in medical image segmentation. We propose the MaxQuery framework for OOD localization. The significant performance improvement of our method on 2 real-world datasets validates its effectiveness. This result proves that interpreting segmentation as query cluster assignment is valid and effective. Our novel MaxQuery and QD loss are also evidently helpful. We believe that the proposed method has the good potential to further boost the adoption of medical image segmentation in designing various clinical applications. Thanks for listening.